Hello AP Chemistry students. Today we are going to be looking at a long FRQ. We have the FRQ from the 2017 AP Chem test, FRQ number 2. And it asks us to answer some questions about the isomers fulminic acid and isocyanic acid. In our first problem, we are given two Lewis dot diagrams, and we must explain why the diagram on the left is a better representation than the diagram on the right, according to formal charges. So this problem requires us to look back at topic 2.6, which is resonance and formal charge. In this topic, we learned that the formal charge for each atom in a molecule is the number of valence electrons that atom normally has, minus the number of assigned electrons that has in the Lewis dot diagram. For our example, we are looking at these two Lewis dot diagrams. So if we transfer them over here, we can look the formal charge of hydrogen, for example. It normally has one electron around it, and in this structure it does have just the one electron, because when it's bonded we split that off into one for hydrogen and one for carbon, so that has a formal charge of 0. If we look at nitrogen though, for example, nitrogen normally has 5 valence electrons, but in this structure it only has 1, 2, 3, 4, so that's 5 minus 4, and that's 1. What we're looking for with formal charge then is the minimum number of non-zero formal charges to figure out which Lewis dot diagram is better suited to represent the molecule. In this example though, they both have 0, 0, 1, negative 1, negative 1 and 1. So we can't use that. But no worries, because if that doesn't work, the negative charge on the most electronegative atom will give us the best representation. So we have a negative charge on oxygen for this one, and we have a negative charge on carbon for this one. So oxygen is more electronegative, so the negative charge being on oxygen instead of on carbon shows us that this would be the better representation, which is what it asks us to explain. Moving on, we are given an equilibrium expression between fulminic acid and isocyanic acid, and we are asked in part B to use the Lewis electron dot diagrams of the two acids and the table of average bond enthalpies to determine the value of delta H for the reaction of HCNO to HNCO. This problem then takes us back to topic 6.7, which is bond enthalpies. In this topic, we learned that delta H is equal to the sum of enthalpy of bonds broken minus the sum of the enthalpies of bonds formed. Because we are going from HCNO, which is fulminic acid, to HNCO, which is isocyanic acid, the bonds broken are the bonds in fulminic acid, and the bonds formed are the bonds in isocyanic acid. So to find the sum of the enthalpies of the bonds broken, which are the bonds in fulminic acid, we add up from the table of enthalpies the bonds that we see in fulminic acid. So we see H to C, find H to C, we add 413 to C triple bonded with N, 891 to N attached to an O, which is 201. We can then add those all up to find that the sum of the enthalpies of bonds broken is 1,505. We can do the same thing in the next isocyanic acid to find that the sum of the enthalpies of bonds formed is 1,751. Then, to find our delta H, we simply take the enthalpy of the bonds broken, which is 1,505, minus the enthalpy of the bonds formed, which is 1,751, and we find that the delta H for this reaction is negative 246 kilojoules per mole of reaction. Now we are ready to move on to part C, which states that a student claims that the delta S for the reaction is close to 0. We're given the task of explaining why the student's claim is accurate. So this takes us to topic 9.2, which is absolute entropy and entropy change. We must recognize that the change from fulminic acid to isocyanic acid does not have any phase change or change in the number of molecules. If we look, they're both gases, and they both have the same exact atoms, just structured differently. The number of molecules and the phase changes in reactions are the two factors that largely or almost completely cause the delta S in the reaction to change. So if neither of those are present, we can expect the S for the reaction to not change, or if it does change, to be incrementally low. So little change in S then is synonymous to delta S close to zero, which is what we were claiming. After part C then, we move on to part D, where we are asked which species of acid is present in higher concentration at equilibrium. We are then asked to justify our answer in terms of thermodynamic favorability and the equilibrium constant. For this question, we have to look at topics 9.3, which is Gibbs free energy and thermodynamic favorability, and also topic 9.5, which is free energy and equilibrium. First, in order to determine thermodynamic favorability, we use the equation delta G equals delta H minus temperature times delta S. Since we've already found in part B that delta H is equal to negative 246 kilojoules per mole of reaction, and we found in part C that delta S is approximately 0, we can then conclude that delta G is approximately delta H, which is then negative 246 kilojoules per mole of reaction. The negative delta G then indicates that the reactants have more free energy than products, which means that the forward reaction is thermodynamically favorable. Further, connecting delta G to K, we look at the equation delta G equals negative RT ln K. This is from topic 9.5, free energy and equilibrium. All we need to know, though, is that a negative delta G indicates that K is greater than 1, and a positive delta G indicates that K is less than 1. Since our delta G is negative, K is greater than 1, and products are favored. Now, in part E, we are given the decomposition reaction of urea, and we are given a graph and table to also represent this decomposition reaction. Our prompt then asks us to explain how the table and graph support a student's claim of the rate law being this. So this problem takes us back to topic 5.3, which is concentration changes over time. And we must recognize from the graph and from the table that this is indeed a half-life reaction. We can see that in time hours, 0, 10, 20, and 30, it's going from 0.1 to 0.05 to 0.025 to 0.0125. And on the graph, similarly, we can see that the curve is representative of a half-life reaction. Because this is a half-life reaction, then it also must be a first-order reaction. And we can see from the student's rate law that it is indeed a first-order reaction. Then, we must determine the value of the rate constant K and include our units. In order then to solve this problem, we must remember that the K for a half-life equation is represented by the equation K equals 0.693 over the time of the half. As we can see from the table and the graph, the half-life is 10 hours. Therefore, we just plug our 10 hours into our K expression and we get 0.069 and then hours to the negative 1 because our hours are in the denominator, or else we can also express that as h to the negative 1. And finally, that brings us to our last part of this problem, F. The student learns that the decomposition reaction was run in a solution with a pH of 13. Briefly describe an experiment, including the initial conditions that you would change and the data you would gather, to determine whether the rate of the reaction is dependent upon the concentration of OH-. All we have to do for part F is design a little experiment, and it's actually simpler than it seems. Since we are trying to determine if the rate of reaction depends on the concentration of OH-, all we have to do is complete the exact same experiment, but with different concentrations of OH-. That is, different pHs. As long as we keep all other variables, such as temperature, constant, then our other experiments will give us evidence if the rate of reaction is or is not dependent on OH- concentration. That's everything then for this FRQ. Hopefully you learned something today and I was able to help you out on your AP Chemistry learning journey. Thank you.